The quest for life depends on the ratio of carbon dioxide to other gases in the atmosphere, with the presence of various biomarkers increasing the chance of life existing. Imagine a scenario with abundant life on heme planets, which are worlds approximately 2 to 6 times the size of Earth, covered by a single vast ocean. These heme worlds represent a new category of planets that intrigue researchers and are technically known as subneptunian planets. Heme water worlds captured attention when the James Webb Space Telescope discovered significant amounts of water and a hydrogen-rich atmosphere on K2-18b. This finding suggests the potential presence of a large ocean and possibly life. K2-18b, an exoplanet with 6 to 8 times the mass of Earth, orbits the cool dwarf star K2-18 within the habitable zone, located 120 light-years away from Earth. Its size is between that of Earth and Neptune, and the presence of methane and carbon dioxide, combined with the absence of ammonia, supports the theory that K2-18b may have a water ocean beneath its hydrogen-rich atmosphere. James Webb also detected another fascinating detail, a molecule called dimethyl sulfide, DMS. On Earth, DMS is exclusively produced by life, mainly from phytoplankton in marine environments. Upcoming observations by Webb are expected to confirm these findings, potentially offering substantial evidence of biological life on K2-18b. This life could range from simple forms like plankton, algae, and microorganisms to more complex beings such as fish or aquatic mammals. The possibility exists that life forms on other planets may surpass our current imagination. Even on a planet completely covered by water, higher life forms might have adapted to living in aquatic environments. The presence or absence of land masses on K2-18b remains uncertain and challenging to determine from a distance. Adding excitement to this context is James Webb's capability to detect artificial light emissions similar to those from cities on distant planets. This ability represents a significant advancement in our search for extraterrestrial life. It is noteworthy that K2-18b was not initially discovered by James Webb. Instead, the Hubble Space Telescope provided the first insights into its atmospheric properties. The promising data from Hubble led researchers to revisit their studies with the new telescope, resulting in rewarding revelations about K2-18b. These analyses are captivating and could mark our first identification of traces of life in space. This revelation is momentous, considering the nearly 100-year search for life within our solar system, which has yielded no conclusive results so far. No life forms have been discovered in our solar system, with only the distant icy moons orbiting Jupiter and Saturn being considered potential candidates. According to researchers, high-end exoplanets could be genuine superworlds and potential cradles of diverse life. Earthly life began in water, with the emergence of land masses and mammals occurring later. If Earth had remained a water planet, intelligent life forms adapted to an aquatic existence might have evolved. Traditionally, the search for extraterrestrial life has focused on exoplanets resembling Earth, specifically smaller rocky planets. However, larger heme worlds are now considered the true superworlds in the cosmic realm. While not all researchers share this optimism, there is a possibility that the oceans on these planets might be too hot to sustain habitable or liquid conditions. In such cases, heme worlds might resemble colossal steam baths. Nonetheless, the existence of life in the hot and toxic thermal pools of Yellowstone Park demonstrates life's adaptability, even in extreme conditions. The exploration of K2-18b raises a compelling question. Can we ever truly determine if the exoplanet is inhabited? If intelligent life were discovered in space, the natural inclination would be to establish contact. K2-18b, located about 124 light-years from Earth, presents a significant challenge for our current space travel capabilities. It takes years for our probes to reach destinations several million or billion kilometers away. A planet 124 light-years away, or even one just 4 light-years away, remains beyond our realistic reach with existing probes or spacecraft. The Voyager probes, launched in the 1970s, will take several thousand years to reach the nearest star systems. Making contact with species in the cosmos would require innovative approaches. The idea of discovering Earth-like planets in our nearby star system, Proxima Centauri, inspired space enthusiast Yuri Milner to design nanoships. These miniature probes, equipped with cameras, are expected to cover several trillion kilometers in a few years, capturing images of planets that might harbor life. If a civilization in space were detected, scientists would likely develop entirely new strategies. Such ambitious goals fuel our spirit of research and innovation. In a hypothetical future with warp drive technology enabling movement through the universe by folding spacetime, traveling to worlds like K218b would no longer be a challenge. However, our current space shuttles operate within the constraints of Newtonian physics and rely on propulsion through propellants and fuels. Even if a spaceship capable of traveling at 10% of the speed of light were built, the journey to K218b would still take 1,240 years. A radio signal traveling at the speed of light would require 124 years to cover the distance between Earth and this distant exoplanet, and a response would arrive another 124 years later. Exploration of exoplanets. The case of K218b. Introduction. The search for extraterrestrial life has long been a fundamental pursuit in astronomy and astrobiology. As technological advancements continue to evolve, our ability to detect and analyze distant worlds has significantly improved. One of the most intriguing discoveries in recent years is the exoplanet K218b, located approximately 120 light-years from Earth. This planet has become a focal point for researchers due to its unique characteristics that suggest the potential for habitability and possibly even life. This expanded exploration will delve deeper into the scientific context of K218b, the technologies involved in its study, and the broader implications for our understanding of life beyond Earth. The significance of K218b. K218b is an exoplanet situated in the habitable zone of its host star, a cool dwarf star known as K218. This zone is crucial because it is the region around a star where conditions may be right for liquid water to exist, a key ingredient for life as we understand it. K218b's size is between that of Earth and Neptune, making it an excellent candidate for studying atmospheric and geological characteristics that could indicate habitability. Atmospheric composition. One of the most compelling aspects of K218b is its atmospheric composition. Observations from the James Webb Space Telescope, JWST, revealed a hydrogen-rich atmosphere with traces of water vapor. The detection of water vapor is significant because it suggests the presence of a substantial amount of water, possibly in the form of a vast ocean. The presence of methane and carbon dioxide further supports the hypothesis that K218b might have a greenhouse effect, which could contribute to maintaining stable temperatures conducive to liquid water. Methane is particularly interesting because, on Earth, it is primarily produced by biological processes. Its presence, along with other gases, helps build a profile of K218b's atmospheric chemistry and could offer clues about potential biological activity. The absence of ammonia, a common toxic compound, is also noteworthy as it supports the idea that the environment could be more hospitable. Technological innovations. The discovery of K218b has been made possible by advancements in space telescopes and observational technology. The James Webb Space Telescope, in particular, has provided unprecedented detail in its observations of distant exoplanets. Its ability to detect and analyze light from distant worlds has revolutionized our understanding of exoplanet atmospheres. James Webb Space Telescope. The JWST is the most advanced space telescope ever built and represents a significant leap forward from its predecessors like the Hubble Space Telescope. Equipped with powerful infrared instruments, the JWST can peer through the thick clouds of gas and dust that often surround exoplanets and their host stars. This capability allows scientists to analyze the atmospheric composition of exoplanets in unprecedented detail. The telescope's ability to detect dimethyl sulfide, DMS, is particularly noteworthy. On Earth, DMS is a molecule produced exclusively by life forms, primarily phytoplankton in marine environments. The presence of DMS in K218b's atmosphere could be a strong indicator of biological processes, suggesting that life might exist on this distant world. The search for extraterrestrial life. The search for extraterrestrial life encompasses a variety of approaches, from studying exoplanet atmospheres to searching for signals from advanced civilizations. The discovery of potentially habitable exoplanets like K218b is a crucial step in this search. Biomarkers. Biomarkers are substances or molecules that indicate the presence of life. In the context of exoplanet research, identifying biomarkers in the atmosphere of a planet can provide evidence of biological activity. The presence of gases such as methane and oxygen, especially in combination, can be a strong indicator of life. On Earth, these gases are produced by living organisms, and their detection on other planets could suggest similar processes. The Drake equation. The Drake equation is a tool used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It takes into account various factors, including the rate of star formation, the fraction of those stars with planets, and the number of planets that could support life. The discovery of potentially habitable exoplanets like K218b adds valuable data to the equation, helping to refine our estimates and guide future searches. Challenges and future prospects. Despite the exciting discoveries, the study of exoplanets like K218b presents several challenges. The vast distances involved and the limitations of current technology make it difficult to gather direct evidence of life. Distance and travel limitations. K218b is located 120 light-years away from Earth, a distance that poses significant challenges for space travel. With current technology, it takes years for spacecraft to reach even the nearest star systems, and traveling to a planet 120 light-years away is far beyond our current capabilities. The Voyager probes, which were launched in the 1970s, will take thousands of years to reach the nearest stars. Innovative approaches, such as the development of nanoships or breakthrough propulsion technologies, are essential for overcoming these challenges. Nanoships, designed by space enthusiasts like Yuri Milner, could potentially cover vast distances in a fraction of the time it would take traditional spacecraft. These miniature probes could capture detailed images and data from distant exoplanets, providing valuable information about their potential habitability. Future technologies. The development of new technologies is crucial for advancing our exploration of exoplanets. Concepts like warp drives, which involve folding spacetime to allow faster-than-light travel, offer a glimpse into a possible future where traveling to distant worlds becomes feasible. However, such technologies remain theoretical and face significant scientific and engineering challenges. Broader implications. The discovery of potentially habitable exoplanets like K218b has profound implications for our understanding of life in the universe. It raises questions about the potential for life beyond Earth and the conditions that might support it. Understanding life's potential. Studying exoplanets helps us understand the potential for life in different environments. By examining the conditions on planets like K218b, scientists can gain insights into the types of environments that might support life and the various forms it might take. This knowledge can inform our search for life on other planets and guide future missions to explore these worlds in more detail. Impacts on philosophy and culture. The discovery of extraterrestrial life, or even the potential for life, has profound philosophical and cultural implications. It challenges our understanding of our place in the universe and can inspire new perspectives on our own existence. The search for life beyond Earth is not only a scientific endeavor, but also a quest that touches on deep questions about humanity's role in the cosmos. Conclusion. The exploration of exoplanets like K218b represents a thrilling frontier in our quest to understand the universe. As technology continues to advance, our ability to detect and analyze distant worlds will only improve, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? The journey to uncover the mysteries of exoplanets, the potential for life, and the broader implications for our understanding of the cosmos continues to inspire and challenge scientists and researchers around the world. Techniques for studying exoplanets. 1. Transit method. One of the primary methods used to discover and study exoplanets is the transit method. This technique involves monitoring the light curve of a star for periodic dips in brightness, which occur when a planet crosses in front of the star from our perspective. The amount of dimming provides information about the planet's size, and additional observations can help determine its orbit and other properties. Kepler Space Telescope. The Kepler Space Telescope was pivotal in the discovery of thousands of exoplanets using the transit method. It identified many planets in the habitable zones of their stars, significantly advancing our understanding of exoplanet demographics. 2. Radial velocity method. The radial velocity method measures the gravitational influence of a planet on its host star. As the planet orbits, it causes the star to wobble slightly. This wobble affects the star's light spectrum, causing shifts towards the red or blue end of the spectrum. By analyzing these shifts, scientists can infer the planet's mass and orbit. HARP spectrograph. The High-Accuracy Radial Velocity Planet Searcher, HARPS, is an example of an instrument used to detect these tiny variations in star velocity, contributing to the discovery of many exoplanets. 3. Direct imaging. Direct imaging involves capturing photographs of exoplanets by blocking out the light from their host stars. This method is challenging due to the brightness of stars compared to the faint light from planets, but can provide detailed information about a planet's atmosphere and composition. Very Large Telescope, VLT. The VLT, operated by the European Southern Observatory, has been used to directly image exoplanets and study their atmospheres. 4. Gravitational microlensing. Gravitational microlensing occurs when a massive object, like a planet or star, passes in front of a more distant star. The gravity of the foreground object bends the light from the background star, creating a temporary brightening that can be detected by telescopes. This method is particularly useful for finding exoplanets that are far from their host stars. OGLE and MOA surveys. The Optical Gravitational Lensing Experiment, OGLE, and the microlensing observations in astrophysics, MOA, surveys have used this technique to discover exoplanets. Broader scientific implications. 1. Astrobiology. Astrobiology is the study of life in the universe, encompassing the origins, evolution, distribution, and future of life on Earth and beyond. The discovery of exoplanets with conditions potentially suitable for life is a significant step forward in this field. It provides a framework for understanding the potential diversity of life forms and the environments they might inhabit. Extremophiles. The study of extremophiles, organisms that thrive in extreme conditions on Earth, helps scientists understand how life might survive in harsh environments on other planets. These organisms can exist in extreme temperatures, pressures, and radiation levels, offering clues about potential life forms on exoplanets. 2. Habitability models. Understanding habitability involves modeling the conditions under which life can exist. Factors include temperature, atmospheric composition, and the presence of liquid water. Scientists use these models to assess which exoplanets might have conditions similar to those on Earth. Venus and Mars comparisons. Studying planets in our own solar system, like Venus and Mars, helps refine models of habitability. For instance, Venus's runaway greenhouse effect and Mars's thin atmosphere provide insights into atmospheric dynamics and their effects on surface conditions. Philosophical and cultural implications. 1. The search for meaning. The search for extraterrestrial life challenges our understanding of our place in the universe. Discovering even microbial life on another planet would have profound implications for our sense of uniqueness and our philosophical and theological perspectives on life and existence. Cosmic perspective. Finding life elsewhere could shift our perspective from being the only known